Oh, yeah, wow, it's a full room. So we're very happy to have Shi Chen, who's going to tell us about a sort of new proposal for the chiral phase transition and massless QCD. So she is a postdoc at University of Minnesota, but is coming to UCSD as a postdoc in the fall. So we'll be nearby. So yeah, go ahead.
Okay. Well, thank you, Theo, for introduction. Today I'm going to talk about something about the thermal phase transition in massless QCD. So we're going to talk about some interesting proposal. And this work is in collaboration with Shi Chen and Robert Pisosky. Okay. So let me first introduce the puzzle that I'm going to address in this talk. So let's consider the massless version of the real world QCD. Namely, so let's consider a 4D QCD with gauge group SUN. I assume NC is always larger than 2. And also let's consider NF massless fundamental Dirac fermions. And I also assume we're like below the conformal window. So we are in the, chiral symmetry breaking phase. So we can consider this kind of quark bilinear operator, which is called the chiral condensate. So at a low temperature, we have non-zero value for this chiral condensate. And we have like a broken chiral symmetry. So we have like gapless modes, which are non-Goldson bosons. So they are massless mesons. But if we raise up the temperature up to some point, this chiral condensate will have a zero value. So we have a gapped phase in high temperature, and we have unbroken chiral symmetry. So therefore, in between, there must be a phase transition somewhere, some TC. Then the natural question is, is this first phase transition first order, or is it continuous? Okay. So like 40 years ago, Robert Pisosky and Frank Wilczek, they proposed some answer to this question. Okay. So they just use the standard Ginsburg-Landau argument. They just wrote down some effective action for the chiral condensate, the order parameter for this phase transition. Okay, so then they solve the phase transition in this system. So let's see, at the mean field level, let's first do mean field. Okay, so look at this term. This is a determinant of the chiral condensate. So when f equals 2, so this is like a quadratic term. And then you change this mu parameter, you will see a second order phase transition at mu equals lambda 3. Okay, and at that phase transition, you have some O4 symmetry. Okay, so we move to NF equals 3. In that case, this term becomes a cubic potential, therefore we see a first order phase transition. If NF is larger than or equal to 4, this term is no longer important, and we always have a second order phase transition at mu equals 0. Okay, so now we have a bigger symmetry, which is like O2 and F squared. So, but this is mean field. We should not trust mean field because we're talking about some 3-dimensional system. So mean field is not trustable. Fluctuations are large. So we need to go beyond. We can try like other methods, for example, like 4 minus epsilon expansion, but also many other numerical simulations. Then people found the following. So when NF equals 2, this mean field second order phase transition is stabilized, and it becomes the O4 Wilson-Fisher safety. But for all larger NF, the phase transition is just the first order. So this mean field second order phase transition is not stable against the fluctuations, so it's gone. Okay, so this is a theoretical prediction. Okay, good. So then what is the experiments? Yeah, of course, because we're talking about massless QCD, so we cannot really have experiments, but we can do lattice Monte-Carlo simulations. Okay, so like in early Monte-Carlo simulations, people find results which agree with those theoretical predictions. Nevertheless, so in recent 5 years, people have like updated a lot of like algorithms, and also they can use more complicated fermion, lattice fermion. So they got like improved results. in those improved lattice results, people found there's no sign for any first order phase transition. For any NF below the conformal window. Okay, so we see there is a disagreement between recent lattice results and the theoretical predictions based on Landau-Ginzburg argument. Moreover, so lattice simulations actually suggest this kind of picture for the phase transition. So let's say, for example, NC equals 3. Then when NF is below the conformal window, we can have this kind of phase transition point. But if we run into the conformal window, so we see the temperature drops. And then we run into the conformal window, and those points are the backstop safeties. So now lattice community somehow believe this kind of picture. Okay. So this is exactly the puzzle. Let's trust the recent lattice results in this talk. So we're going to ask, can this second order phase transition go beyond the Ginzburg-Landau description at all? If it can, so which 3D CFT may describe this beyond Landau phase transition? Okay, so this is a question of this talk.
Explain the first question. What does that mean?
Sorry?
What do you mean by this?
Oh, I mean, because people use Ginzburg-Landau argument to study this phase transition, but they give some wrong results, right? So then we must go beyond that argument. So do we really have such a thing? Oh, that's the first question. Okay. So let me continue. Okay, then let's review the symmetry and the anomalies of the QCD system, because we know symmetry and anomalies are very important for us to understand the strongly coupled quantum theories. Okay, let's review them. So in 4D, I mean zero temperature, the massless QCD has this symmetry. So this is a baryon symmetry. These are like the so-called chiral symmetry. And this symmetry has a Louvet anomaly, which is described by this 5-dimensional invertible field theory. So here I turn on like U1 baryon H field, which is AB and also AR, AR for chiral symmetries. And this is invertible theory in 5 dimensions. So these guys, these first two guys describe the sailable anomaly of AL and AR. When AF is larger or equal to 3, this is actually just the 3-dimensional Chen-Simons partition function. When AF equals 2, it's actually the 5-dimensional spin Bordizan invariant associated to the Wheaton anomaly. Okay, so that's the first part. So we still have a second part, which is about a mixed Louvet anomaly between the baryon symmetry and the chiral symmetry. Okay, so in this talk, this part will play a more important role. Okay. So as Thomas showed us yesterday morning, exactly on this board, matching this anomaly requires massless degrees of freedom in the physical spectrum. So if NF is too large, so we're in the infrared free region, then this anomaly is matched by massless quarks and gluons in the infrared. If we are in the conformal window, then this anomaly is matched by the backstop safeties. If we continue to lower down NF, so we run into the chiral symmetry region. So the anomaly is matched by non-gluous bosons, which are mesons. So this is a symmetry breaking pattern in this region. So this is the flow symmetry with baryon symmetry and chiral symmetry. So it's spontaneous broken to a subgroup. Okay. So therefore, in this region, the infrared physics is described by a nonlinear sigma model with this target space. Okay. And let's see precisely how the anomaly is matched in this nonlinear sigma model. So for the first 2 terms, which are about the self-anomaly of chiral symmetry. So these are matched by with luminous Wheaton terms in the nonlinear sigma model. When AF equals 2, this with limit weighted term is reduced to some spin origin thing. It's a set angle. Yes. The second part, the mixed Hooke's anomaly between baryon symmetry and chiral symmetry, is matched by the following effect. So we can identify the Stern symmetry associated to this homotopy group of the target space as the baryon symmetry. If we do that, we turn on background gauge field in this non-unicycle model, we can reproduce this anomaly. Okay, so this is now standard story in 4D QCD. Okay, so now I'm going to raise up the temperature of the system. Okay, so I think this is now. Let's put the system on R3 times S1. So for a 4-dimensional gauge field, it like splits into 2 parts. So along the spatial dimension, we have like 3D gauge fields, but we also have some other parts which are like holonomies along the S1 direction. So those things are scalar fields with value in the gauge group. Okay. So with this kind of splitting, the 5-dimensional invertible theory is reduced to a 4-dimensional invertible theory, and we have this kind of dimension reduction. So the self anomaly of chiral symmetry is gone. It's not there at finite temperature, but the second part, the mixed Hooke anomaly between baryon symmetry and chiral symmetry, survive in a weird way. So this AL and AR are still gauge fields, but this AB is the holonomy field. Okay. So what does this mean? So
anti-periodic one. This is thermal.
Yeah, thermal. So yeah, so yeah. So what does this invertible theory mean? So on a closed spin manifold, I mean 4-dimensional, this is well defined, of course. But if this 4-dimensional manifold has a boundary, this is no longer well defined under the shift of theta b by 2 pi. So therefore, the partition function of the thermal QCD must satisfy this equation. So if we turn on background gauge field for chiral symmetry, and we shift the baryon holonomy by 2 pi, the partition function is not invariant. It comes with like some additional terms. This term denotes the 3-dimensional transons. Okay. Therefore, we have some kinds of anomaly in this system, and people may call it like anomaly involving coupling constants, or people can say this is an anomaly about some -1 form symmetry. Anyway, it's just terminologies. The physical thing is just this equation. Okay. Okay. So before we proceed, so let me explain the physical significance of this theta b. So this theta b actually has a physical meaning at finite temperature, which is related to the chemical potential for baryons. And it contributes to an imaginary chemical potential. And a lot of people like this because this kind of imaginary chemical potential has no sign problem. So they can really simulate systems within this imaginary chemical potential. Okay. So remember this equation. So let's take theta b, for example, to be like minus pi. Then minus pi plus pi, 2 pi is actually pi. So we can have, but the pi and minus pi are equivalent under shift of 2 pi. So we can imagine at theta b equals pi, this anomaly is enhanced to some a more ordinary anomaly about some discrete symmetry. So let's consider the discrete symmetry. We can have like 3 kinds of discrete symmetry. So the first is charge conjugation. The second is a reflection about the S1 direction. The third is a reflection about some R direction. Actually, there are many different reflections, but we just picked up some generators. Okay. So when theta b is 0, all the three generators are root symmetries. So we have a Z2 cubic symmetry. But if we turn on non-trivial theta B, so some generator is broken because some discrete symmetry will flip the sign of theta B. Okay, so now we just have like a Z2 square symmetry. Okay, but if we move to theta B equals pi, the symmetry get enhanced again. Nevertheless, now it comes with some adhuved anomaly coming from this relation. If you take theta B equals pi, you will see that. Okay, so we see that at final temperature, massless QCD has some anomaly. So we need to match it. The infrared effective theory in 3D need to match this anomaly. So in high temperature limit and in a low temperature limit, we already know how the anomaly is matched. So first of all, at low temperature, if the temperature is very low, so we can believe the chiral symmetry is still spontaneously broken. Therefore, the infrared theory is still described by a nonlinear signal model with this scalar field. The only difference is that we are talking about 3D effective theory with scale that is much larger than beta, inverse temperature. So therefore, we have a three-dimensional nonlinear signal model. And this theta B appears as a set angle for this nonlinear signal model. So this is Sherman current related to the pi 3. Okay, so this is what happened at low temperature. Then what happened at the high temperature? At high temperature, it's even better. So because we can really do perturbative calculations at high enough temperature. Robert and Weiss did this many years ago, and they found that there is a first order phase transition at the theta B equals pi, and it's related to this symmetry breaking pattern. Remember that at theta equals pi, we have this Z2 cubic symmetry, and it has some anomaly, and now it's spontaneously broken to an anomaly-free subgroup. So that gives this first order phase transition. Okay, so now it's clear how the anomalies matched at high temperature and low temperature. The question is now, what happened in between? So
this transition is independent of the
sorry?
This is first order transition is independent of the index.
Yes, independent of that. And also, yeah. And this system is always kept, even at the phase transition. Of course, this is for like high enough temperature where you can believe perturbative calculations. Good. So, as I said at the beginning of this talk, I choose to believe recent lattice results. So I choose to believe, oh, there should be a critical line of continuous phase transitions that separates this high temperature phase and the low temperature phase. Then I'm going to ask, what kind of safety can live on the line so that it can match the anomaly?
Sorry, the last results are just the theta equals 0 or all theta?
Okay, good. So the last result I just showed only cares about theta equals 0, but we do have some new lattice results like last year and this year. They study this whole line, and they agree that, okay, they always see second order transition. Yeah. But I have to say that it's quite preliminary, and people should improve it to see more convincing results. Good. Anyway, I choose to believe the lattice indications in this talk. Okay. So then we should consider what kind of safety can live on the critical one. Before going to that part, I need to explain a small technical detail here. The thing is, now I have this theta P. But as I said, theta P is imaginary chemical potential. So somebody might worry, oh, does it cause some problem, like a unitarity problem or something like that to this safety? The answer is of course no. Okay, so because we can have like different Hamiltonian interpretations for a circle compact field theory. So typically we consider this kind of Hamiltonian interpretation. We take R3 to be space and take S1 to be the time direction. So then we have a thermal system, which is a grand canonical ensemble. But instead, we can also consider a different Hamiltonian interpretation. We take like R2 times S1 to be space, but take some R direction, some extended direction as a time. Okay. Then we can check what kind of property are preserved in these two different interpretations. So in the thermal interpretation, as I said, this T times theta B gives imaginary chemical potential. Therefore, the reflection possibility that reflects S1 direction is indeed violated. So we lose unitarity in some sense. Okay. And this free energy has a physical meaning as thermal pressure, the grand potential density. And this will be this operator, which is the zero frequency mode of the baryon density times with an I. So this operator is anti-Hermitian because of the presence of this I. So this is what happened in the thermal interpretation. Nevertheless, in the second interpretation, we have like a zero temperature quantum system. And if we check the R reflection positivity, it's okay, it's preserved. So from this point of view, the system is still unitary. And this setup B has a physical interpretation as some baryon AB phase along this spatial circle. And this minus F, the free energy, has the physical meaning of Casimir energy density. Yeah. And more importantly, this rho B is actually Hermitian. Yeah. So this is some subtlety about the Hamiltonian interpretations. But for any physical observable, like partition functions, correlation functions, everything, all of them should be simultaneously interpretable in both Hamiltonian pictures. Okay.
I think maybe I missed this, but like in 4D, I can both turn on a real temperature and a real chemical potential.
Oh yeah, you can do that, of course. For example, if you turn on real chemical potential, you save this one. You save the reflection positivity about the S1 direction. But then you kill the R reflection possibility in the second interpretation. You can only preserve one of them. Because in that case, this AB phase will become some real variable. So it gives something not good.
That's what we have sometimes when we go to QCD.
Oh yeah, I mean, yes, of course. Because we, for thermal purpose, we only care about this picture. Of course, yeah. Here, I want to emphasize the following thing. So if we talk about the three-dimensional EFT, the second picture is more convenient because we hold the three-dimensional EFT to be a three-dimensional QFT on its own. So it must have some Hamiltonian interpretation as hyperspace, unitarity locality, and everything. So therefore, this second interpretation is more convenient for that purpose, especially on the critical line. So if we talk about the IR 3D safety, then this is a more appropriate picture. Okay.
Why don't you just stick to Euclidean signature where everything is?
Oh, yeah, this is Euclidean signature.
Oh, this is not Euclidean.
Interpretation. Yeah.
In Euclidean signature, you have everything you want at the same time. There's no problem.
No, there is a problem. I mean,
You're just studying a theory, Euclidean signature on a Euclidean circle. You put the standard Wilson for the Euclidean relation. Then you can quick rotate in either channel and get you components.
you can interpret this as two different rotation, of course. Yeah. But for example, here, the partition function has a meaning of like trace e to the minus beta h, right? And this has a different Hamiltonian interpretation. Yeah. You can say I'm doing rotation. Yeah. But the point is actually the unitarity. So I just want to emphasize on the critical line, the 3D infrared safeties should be unitary. for any set of B, for any real set of B. But of course, if you make set of B to be imaginary, or say you consider real chemical potential, this is not guaranteed. Okay. Okay, so then let's move on. Let's see how we can match those anomalies on the critical line. So the IR physics on the critical line must change as we vary set of B from 0 to pi. That's required by the anomaly. And then we can consider two different types of change. Either the physics can change suddenly, or it can change smoothly. So this is like the high T phase. This is like the low T phase. Okay, so let's first talk about this possibility. So we can minimally we can consider just some sudden change at the slot of this pi. So this sudden change can be either first order or second order. Then we have like these two possibilities. So here it means we have like a first order transition on the critical line and slot of this pi. And here we have a second order transition on the critical line at the set of equals pi. Okay. And this TC prime, this dot is just icing. But this red dot should be something more complicated, which convex matter physicists would call it the deconfined quantum critical point. Okay. Moreover, this blue line should be described by the Landau-Ginzburg description, because the anomaly is saturated by the physics around the set of equals pi, just like in the high T phase. Okay, so therefore I call this scenario as Landau scenario, this scenario as Landau DQCD scenario. Okay. For NF equals 2, these two scenarios are okay. There's no problem about that. But for large NF, as I showed at the beginning, the Landau-Ginzburg description cannot give us a second order phase transition, cannot give us a critical line. So therefore, for large NF, for the moment, we should not trust these two scenarios. Now let's move to the third scenario, which corresponds to the smooth change on the critical line. So I use like a rainbow color for the critical line. Different color means different safety data. So therefore, this critical line is from a conformal manifold, and this direction, the tangent to this critical line, corresponds to exact marginal deformation. Yeah, this is a very weird scenario, so I'm going to like talk about it later. But for the moment, let me summarize. According to the symmetry and the anomaly, so minimally we can have like three scenarios, but of course we can have like more complicated scenarios. For example, you can enlarge this dot into a gapless region. Yeah, some people like that. Okay. Anyway, so for NF equals 2, all the three scenarios seem okay. Okay. So for large NF, so far only this scenario hasn't been excluded. So we're going to focus on this last scenario to see if it's really feasible or not. Okay.
Why can't it be the same CFT along the line? Why does it have to be a conformal manifold?
You mean like just the same color? Yeah, because then we cannot match the anomaly. The anomaly requires this to happen. Yeah.
Why not two CFTs, the left and the right?
You mean this is safety?
Yes.
This is safety?
Yes.
Okay, now you see these 2 points are the same points, right? So it's a multi-critical point, like joining two different safeties. Yeah, that's a non-minimal scenario. It's more complicated. Yeah.
Are you saying that the lattice can actually map this phase diagram for real QCD? Or like some
You mean massless QCD, right?
massless?
Yeah, so we must focus on massless QCD, otherwise you won't have phase transition. Yeah. So, but you're right, on the lattice, people can really simulate this setup because there's no sign problem for that. Yeah. So in principle, if people work hard, they can similar with recycle. Okay, so actually, people do have some results already. They tend to exclude this first possibility.
Why?
Because lattice people find these two phase transitions should be the same point. There are like a few recent papers on this. So yeah, so people tend to think that these two cases are more plausible. Yeah, but I don't fully trust those papers. I think some further studies definitely.
It's very hard, but the blue thing, they're supposed to be second order. Black thing is also second order.
Yeah, but they somehow can measure like they just pick up like different beats around the spot to see the tendency, and they see like the flat behavior, and they don't see any lower critical point. So that's what they observe.
They measure the critical exponents of Y.
No, they can't. Because that's too difficult on lattice. So they have some constraint, but that bound is super wide.
And use for massless fermions.
They cannot directly do massless fermion. So they like turn on some small fermion mass and then reduce the mass of the fermion. And that is good because turning on a small mass actually means to turning on a small, something like a magnetic field, right? So you introduce some magnetic field to a system, like in the Ising model. So you can actually measure some critical exponents from this kind of scaling. Yeah. Okay. Okay, so let me move on. So I only have 20 pages. So the rest of the pages are all about this last scenario. So if you have like question about the first two scenarios, please ask this at this moment or after the talk. Yeah. Okay. So the last scenario is super weird. I cannot say that, oh, yeah, we just believe this is true. No. It's highly non-trivial. We need some evidence at least. So the last scenario requires the existence of a conformal manifold of 3 DCFTs. So for the moment, let me give a name to this CFT. I call it SUMF setup B. And the conformal manifold has this topology. These 2 points, theta b equals 0 and theta b equals pi are the 2 ends of this conformal manifold. And the discrete symmetries are enhanced at these points. Everywhere else on this conformal manifold has a smaller discrete symmetry. Okay. So let's look at the spectrum versus the expected spectrum of this safety, this weird safety. So first of all, we should have some relevant singlet to which the T perturbation, the temperature perturbation should flow. Second, we should have some relevant order operator to which the chiral condensate should flow. Third, we should have some exactly marginal operator to which the rho b, the baryon density, should flow. So this operator, this exactly marginal operator, generates this conformal manifold. But we know that non-supersymmetric 3D CFTs with conformal manifolds are very, very rare. And to be honest, I don't know any really reliable example of this kind of thing. So does this CFT really exist? So it's a question. And I'm sorry, I'm not gonna prove this in my talk. I'm not powerful enough to do that. So I will just show you some preliminary evidence for that. I will explain to you why I believe probably this can be true. Okay.
What's the non-reliable example you know?
Sorry?
What's the non-reliable example you know?
Well, so for example, some radius type construction.
That's large N. Large N.
Yeah, that's large N.
No, you don't have that.
Yeah, I don't have that. Yeah, but for supersymmetric case, you have examples like consider H2. Yeah, you can have like CP1 conformal manifold. Yeah, but for a non-supersymmetric case, yeah, it's hard.
They're not even like bootstrap candidates. It's not bootstrap islands.
I will talk about that later.
Oh.
Yeah, hold the thoughts for a moment. Yeah. Okay, so let's play a bit with this assumed safety. So let's first add the temperature deformation, okay? And then for some sign of this coefficient mu, this system should flow to a database. And for the other sign of this mu, the system should flow to a number surface, which is IR Gaussian safety, okay? So then this, the theory with this deformation, I would call it the SUNF theta field theory. So this field theory should describe the IR physics of the entire thermal massless QCD. Okay. And then we know that the IR tail of the arch flow in this region should be approached by the 3D principal chiral model, the nonlinear circle model I mentioned earlier. Okay. And moreover, we know that at theta b equals 0, this nonlinear circle model, the principal chiral model, has a non-trivial UV fixed point in fractional spacetime dimensions, which is 2 plus epsilon. And it also has like similar arch flow behaviors like this. So how is that possible? So we know that in 2D, nonlinear circle models are asymptote free. And if you see the arch flow, it flows to a UV Gaussian fixed point to some strongly coupled region, which is gap. Actually, because 2D principal chiral model is integrable, you can solve the system, find all the scatter metrics and so on. So people indeed confirm, oh, this is the delta phase. Okay, so if we slightly change the dimension, we consider 2 plus epsilon dimension, then this fixed point splits into 2. So we still have a Gaussian fixed point, but then we also have a new interactive fixed point. So the distance between these two fixed points is of order epsilon. Okay. So we say this point is a UV fixed point. So if you go this way, you flow to the Gaussian. If you flow this way, you flow to the database. So this is very similar to the this behavior. Okay. So then the question is, do we have a conformal manifold here? Is this UV fixed point? You mean this one? You mean this? Okay, okay. I'm
you getting that? I'm sorry. Are you going to say something about it?
Okay, I'm going to say.
I thought you were moving on.
No. Okay. So the question is, do we have like an exact margin reformation in this UV point? The answer is yes. According to some recent paper by Slava and Fabiana, so they study this kind of 2 plus epsilon dimensional nonlinear circle model. They study the fixed points. And they argue that the topological current, the closed skirming 3 form, is actually a primary operator with protective scaling dimension of the exactly 3, no matter what epsilon is. Okay. So therefore, this kind of if we can extrapolate epsilon to 1, then this skirming current, the skirming 3 form, is actually a good candidate for the exact marginal information. Okay. So I will go back to this paper later, but let me first move on. So therefore, I tend to think the 2 plus epsilon dimensional UV fixed point of the PCM is a natural candidate for the 3D CFT at a theta 0. And also, moreover, the 2 plus epsilon dimensional PCM might also be a natural candidate for the entire 3D field theory at theta 0. Okay. So good. So let's go back to your question.
Well, I was going to ask, this should break down if NF is sufficiently large, right? Because you enter the conformal phase.
Exactly.
Can you see that in the 2 plus epsilon?
We don't see that. So you should not believe that this is valid always. There are like two levels of question. The first is the existence of this CFT in the principal current model. So that's question one. Okay, the question two is, is it realized in QCD? So my answer to your question two is of course no. Yeah, not necessary. But probably for question one, the answer is this. Okay, then continue. So what about conformal bootstrap? So the most reliable technique we now have for 3D safety. Let's see. So first, let's try to do the higher loop calculation for this 2 plus epsilon expansion. We just borrow those results from some old papers because at that time it was quite interesting to study this kind of model. So we have like 4 loop results for the scaling dimension of the energy operator, which corresponds to the temperature prediction. Then we also have like 3 loop results for the order parameter operator. Okay, so then we can try to do some very bold extrapolation using some Padebaro summation. This step is super bold. If you don't trust it, I'm totally fine. But it's better than nothing. So let's try what we can find. So we find this table. So we see that the results have large error bars, as it should. So this is okay. So and we see that these 2 operators are indeed like relevant operators. And according to their scaling dimension, and also we don't see any sign of like the violation of unitarity bound. Okay.
Say why for the energy operator you have higher error borders, but the error is much larger than
Okay.
right?
Okay, so the thing, this is some weird feature of the Padebaro summation, because when you do the Padé approximation, so this kind of, you see, you have like the same sign for all the terms. That will give a larger uncertainty in the Padé approximation. But this has like alternating behavior. It actually has a smaller uncertainty in the Padé approximation. So I admit this is a weird feature. Okay, good. So then,
Just plug in epsilon equals 1 without doing the Padé summation.
Uh,
Okay, then 2.
I'm sorry.
Just plug in epsilon equals 1. Don't use the summation. You still get everything. Is everything okay?
Yeah, it's.
Even though all the signs are negative, you don't get violation of unitarity.
I don't think so. Yeah, I don't think so. You get the violation. We can just do that, right?
I think what zeta of 3 is.
You mean here? That is Riemann Z function.
What is I'm saying there's no violation of unitarity. You just plug in epsilon equals 1.
Yeah. Okay, so yeah, let's compare with like conformal bootstrap. Yeah, so when f is true, we have a lot of data from conformal bootstrap because the PCM with NFX2 is precisely the O4 non-linear model. So if people study like Wilson-Fisher exponents, people will study that model. Okay, so in this famous paper, they have an island that constrain the O4 universality class in 3D. And this kind of data, of course, we say that it overlaps with the island. And but for larger NF, I don't know, probably conformal bootstrap people just don't care about those systems. There are few studies on that. So there is only one relevant paper which did a conformal bootstrap for NFX3. And they did find a non-trivial rough kink at this place. So, and there is a very, very preliminary agreement with these 2 things. Okay, does this prove anything? No. But this preliminary agreements do suggest probably future careful studies are worth trying, especially for large NF.
Bootstrap paper, surgery paper, they don't have a margin.
They don't have that. They don't include that in their like relations, but they also don't exclude that kind of thing in their algorithm. Yeah, they actually study a much larger symmetry.
But if they have around the king, they should be able to tell the spectrum is approximate.
They didn't do that in the paper. So as I said, this result is very preliminary. So definitely we need to improve the results on this. You said this is like 10 years ago, and no progress after that. Nobody followed this kind of thing. So we hope like our paper can draw some attention, can make some people be interested to do conformal bootstrap for this kind of model.
You don't expect that if there is this marginal operator, like, I guess I don't know, we don't know what the scaling of it is, but if it's close to what you're
Margin.
It's user margin.
But then wouldn't you expect it something that goes haywire if you don't do these things so
How is the light spectrum for a king?
Yeah.
So you should be able to see it with the naked eye almost.
Yeah, you need to work hard. Yeah. Okay. So, all right. Okay, this is the last slide of my talk. So let me summarize my talk. So basically, we made two conjectures based on very preliminary evidence. First, we conjecture some one parameter 3D unitary safety family exists. Second, we conjecture that finite temperature massless QCD flows to this conformal manifold at the chiral-based transition. Okay. We need to find more evidence, more convincing evidence. For the first conjecture, we need improved conformal bootstrap bounds and improved epsilon expansion knowledge and so on. For the second conjecture, we need like improved lattice simulations, and we need to measure the critical exponents of lattice, especially those about this rho B, about the exact margin operator. Okay, so these two conjectures are not independent of each other. They're related. If we can prove B, then we should prove A. If we disprove A, then of course we disprove B. So they are related. So we relate like a question on the safety side and also a question on the QCD side. So that's all about my talk. Thank you very much.
The strongest argument is Svishkov's paper,
Yeah.
but Svishkov, I thought only for one specific value of an he has a operator for dimension 3, right? The parameter bit.
Oh, yeah. Because he's studying like a OM model.
Yes.
So
In your
only
case, it's always 3.
Huh?
In your case, it's always going to be 3. The dimension
I mean, 4. It's a 4.
Right.
Okay, so let me write something. I mean, their papers study like OM model, and our papers study like this target space. Okay, so I should not write this. The target space is actually SM. Okay, so I mean, S3 is the same as S2, of course. So we overlap on this particular piece. But yeah.
Oh, so you don't have an argument for an exact margin information for any of it?
No, we have. But I mean, that's not included in Sava's paper. Because they talk about this kind of thing.
Yes.
It's different.
Yes. So in your case,
Yeah, there is always an exact margin differential. Yeah. Because this is always
But it's not exactly rho B, right? There's some, it mixes with the temperature.
exactly. So let me show you this. You see, so
The slope starts out at 0.
yeah. So at theta equals 0 and theta equals pi, because we have enhanced discrete symmetry. So these two deformations do not mix.
Sure.
But the areals it mixes. So it becomes like tilted with translation lines. There's no further questions.
I did this discount NC equals to what is you said NC greater than or equal to 3, right? This whole story of NC.
Oh, okay. So at the beginning, already.
Yeah. So what happens at NC equals to?
Oh yeah, at NC equals 2, the symmetry of the system is no longer this one.
That's fine. But what is the picture of the baseline?
Okay. So you have a much bigger symmetry G, and you cannot distinguish mesons and baryons. And you still have like this kind of phase transition, but we didn't study that case.
What is lattice?
There's no UMN barrier.
Yeah, there's no baryon. Like this becomes some B group. I forget which one, SU or SQ. Oh yeah, anyway.
That's SU big, like SU everything.
Yeah, SU like Q and F, something like that. Yeah. So anyway, so you see the symmetry pattern is very different. So you should expect different physics.
But do we have lattice evidence of what the picture looks like then?
Oh, I'm not sure about that.
Is there even a Robert bias phase in the case? Even at very high temperature?
To be honest, I don't think so because we don't have
Yeah,
therapy.
there's-
Yeah, we don't have therapy.
Oh, so there's no phase transition even at infinite temperature.
I think so. Yeah, but I need to check the details. Yeah. But, yeah. So anyway, the physics should be very different.
The question? Let's think Shi.
Sure, you could just turn on the Wilson line inside that SU2